Okay, so thank you for the introduction, of course, and the invitation. So as the ridiculous title suggests, this will be a continuation of my short postdoc member talk. Again, about the very classical restricted three-body problem. So I'll try to give some flavor of what we're trying to do, both from the theoretical side and also with some view towards practical applications. This was an interesting problem, say, at the time of Newton. It was still a very fantastic problem at the time of Poincaré, which was much later. And by the end of this talk, I hope that I managed to convince you that it's still a fantastic problem to look into today, armed from the modern perspective. Okay, so let me remind you about the setup. So we start with three objects, the Earth, the Moon, and the satellite, and they have certain associated masses, and we'll just leave them to interact with each other according to Newton's law of gravitation. Okay, so this gives us some very complicated dynamical system, and we're trying to make sense of it. And there are some classical assumptions that people have made in order to simplify the situation a bit. So first of all, we can look at the restricted case, in which we assume that the mass of the satellite is 0. So it's negligible when we compare it to the other two, which are called the primaries, right? So those are the heavy masses. So the satellite is affected by the primaries, but not vice versa. Okay. The circular case, we assume that the primaries, the Earth and the Moon, they actually move in circles around the common center of mass, as opposed to the more general case in which they move in ellipses, right? So this is the two-body problem, very classical problem, already appears in Newton's Principia, and it's a very beautiful problem already. The planar case is when we assume that the satellite moves in the plane containing the Earth and the Moon, and the spatial case is when we drop the planar assumptions, and now we allow the satellite to move wherever it wants to, okay? So the goal is to study the motion of the satellite under the influence of the big masses, okay? In a broadly understood sense, but of course, as we go along, we have to make, in some sense, concrete questions to attack. So this is a picture always to remember, the Earth, the Moon, and the satellite whose dynamics we're trying to understand. So of course, this is a Hamiltonian problem. And because of the assumption that we made on the rotating motion of the primaries, we can actually join them in their motion. So we can change coordinates in such a way that they accompany the rotating motion. So now the Earth and the Moon are fixed. And the magic of this change of coordinates is that the associated Hamiltonian becomes time independent. Right? So it is a conserved quantity of the motion. Okay? And we can write it down explicitly. There's some kinetic term associated to just the free motion, but then there's also some gravitational potentials, one for each of the primaries, the Moon and the Earth. And then the price we pay is this change of coordinates is the appearance of this angular momentum term, this one, which is keeping track of the rotating frame. Okay? But the really nice thing is that there's no time dependence. Okay? Here we usually normalize in such a way that the sum of the mass of the Earth and the Moon is 1. So this new parameter, which is normal the mass ratio, you should think of as the mass of the Moon. The planar problem is precisely when we drop the last two coordinates, P3 equals Q3 equals 0. So this is the flow invariant subset. So here Q and P are coordinates in R3. So Q is position in R3, P is momentum in R3. So this is a 6-dimensional problem on the nose. So phase space is 6-dimensional. So the two parameters in the problem, mu, and the second parameter is the Jacobi constant, which is we fix the total energy of the system equals to C. Okay.
Where is P3 and Q3 in that H? Sorry, P3 and Q3, where are they in the H?
So this is the third component of Q.
Okay.
And the
but
third
the
component.
angular momentum never depends.
And the angular momentum, this is important, only depends on the first two.
Okay.
So this is why this is an invariant subset.
Okay.
Okay. Any more questions before I go on? Okay, so if you do more theory with respect to this Hamiltonian, you will find that there are precisely 5 critical values, L1 to L5. They're classically called the Lagrangians. So they were actually found by Euler and Lagrange many years ago. In this picture, what you're seeing is I'm graphing the critical values of the energy of each of them. So the horizontal axis is the mass ratio, the vertical axis is the Jacobi constant C. And for example, everything that's below H of L1, which is the lowest critical value of the energy, is what we call the low energy range. And here at mu equals 0, so the vertical axis, you should think, well, there's no moon anymore. So I switched off the moon, but I still remember that I'm in a rotating frame. So this is usually called the rotating Kepler problem, or the two-body problem in a rotating frame. Okay? This is actually an integrable system. And then there's a fact that as you go to minus infinity, you recover the actual non-rotating Kepler problem, so the honest two-body problem, after some regularization that you have to do. So these are the two limit cases which are integrable systems of interest in the problem already. So there's a modern theory which was proven not so long ago, and it is the starting point for the modern contact geometry that we can do in this very old problem. And it was proven by a number of people in the planar case, so Peter Albers, Urs Frauenfelder, Otto van Kurt, and Gabriel Patterna in 2012. The spatial case was dealt with by Cho, Jung, and Kim, more recently 2019. Roughly speaking, all it says is that if you're in the low energy range, so if the energy is low, then after you regularize collisions and compactify the level sets, then actually what you get, the level set of energy C is actually a contact manifold, either near the Earth or near the Moon. Okay? So the contact geometry of this level sets is standard, so we completely understand it. That's not a moving part of the problem, which is good, right? Because what's interesting now is the dynamics, which becomes a ray flow. Okay.
I have a question.
Yeah.
What do you mean by regularized?
Okay, that's a good question. So what I mean there, if you look at I've explained this a bit in the short talk. I don't want to go into too many details, but if you look at this Hamiltonian, it's actually singular when Q equals m or Q equals e, which means that the satellite crashed. And now, when you crash, conservation of energy for this Hamiltonian tells you that the velocity needs to explode. So your level set actually is non-compact. So regularization means a procedure by which you compactify the level set. So now we have some dynamics on some closed manner. Okay. Any more questions? Okay. So the new direction in this picture is we'll try to use modern methods coming from symplectic and contact geometry, holomorphic curves, Floer theory, you name it. Okay. All the toolkit that we have.
What do you mean the contact geometry standard?
It's the topology of the manifold is just S2 times S3, which is the unit cotangent bundle of S3 with its standard contact structure. But the ray dynamics, it's very much non-standard.
Like which ray flow you're choosing is not the standard.
Exactly. I mean, you're not choosing it, it's given.
Yeah, yeah.
Okay, so let me go down the years sort of what Poincaré was actually trying to do, tell you a bit about the history of this ideas that come from such a long story of this problem. So, you know, back in the day, Poincaré was actually studying the planar case, which historically has played an important role in dynamics. And one of the first things that, you know, they already told you that you should try to do whenever you're given a dynamical system, the first thing you should try to do is find orbits or critical points if there are any. I mean, this we know from, you know, when we're studying differential equations at the undergrad, right? We're given a differential equation. The first thing that we want to do is find the critical points. And then because we can draw the phase diagrams and whatnot, so critical points of orbits somehow organize the dynamics. They're the skeleton by which everything around moves. So that's the first thing that I want to do. So in this direction, Poincaré's approach can be reduced basically to the following two steps. So the first step is finding what's called a global surface of section for the dynamics. So what you should imagine is that you have this three-dimensional level set in the planar problem. I mean, first of all, you start with a four-dimensional phase space in the planar problem. When you fix the energy now, that's three-dimensional. Right? So we have some dynamics on a threefold. The spatial problem, you start with a six manifold, and then you fix the energy, and now you have dynamics on a fivefold. So this is a planar problem is co-dimension 2. But in the planar problem, where everything is three-dimensional, imagine you have a dynamics in this threefold, and now a global surface of section is just an embedded surface inside the threefold with the property that its boundary is a collection of closed orbits, and that every point which is not in the boundary of the surface, its orbit will intersect the interior of the surface at some point in the future and at some point in the past, transversely. Okay? So you should think, I always say this, you know, you should think of it as a hand that you put that it intersects all the orbits. So your hand has to be big enough. This is why the global comes in. And it's a section, well, because the section, what it gives you is you start with some continuous dynamic on a threefold, and you basically reduce everything to studying the discrete dynamics of the return map on one dimension less. Right? So this is a reduction of the degrees of freedom that we've been taught that is something that we should look for in this kind of problem. So this motivates the second step, right? Because if you have the surface, you can follow the orbit of every point on the surface, and then you look at the first return point. This gives you a map called the Poincaré return map. By construction, the orbits in the ambient threefold are in 1-1 correspondence with periodic points of the return map. Okay? So if you're able to prove a fixed point with this return map, then you're in business because you found plenty of orbits. This is, of course, the setting of a very famous term, the Poincaré-Birkhoff theorem, which is a statement about a map on the annulus. So imagine having an annulus embedded in your threefold such that there's a twist condition, so the return map moves the boundary in opposite directions, then Poincaré-Birkhoff tells you you will be able to find plenty of orbits. Okay. So the goal for us, or one of the goals that we can set for ourselves in this setting, is we'll generalize this classical approach from the planar problem to the spatial problem. How does this look like in high
When you say orbit, you mean periodic orbit?
So in order to do that, I need to talk a bit about what an open book decomposition is. This is some topological or smooth notion. So an open book decomposition on a manifold M is just a vibration defined on the complement of some codimension 2 submanifold B, taking values in the circle, with the property that it should look standard as some color neighborhood of B. So color neighborhood is just a thickening of B inside the ambient manifold, B times D2, and I want that my variation is just the angle coordinate on some choice of polar coordinates on the D2 factor, normal to the submanifold B. This data of vibration is abstractly determined by two pieces of data, the page of the open book and the monodromy, so P and phi. So P here is just a closure of a fiber, and B is just the boundary of every fiber, which is usually called the binding of the open book. Phi here is just another piece of data, which is the monodromy, is just a diffeomorphism of P onto itself, which is the identity of the boundary. So if you give me these two pieces of data, I can abstractly cook up a manifold for you, M. And alternatively, if you give me a vibration, then M is also presented in this way. So the two notions are actually equivalent up to isotopy, but if you're doing dynamics, which is very sensitive to isotopies, you should better talk about concrete vibrations in this sense. But the abstract notion is also important whenever you want to understand what the topology of everything is actually is. So I'm gonna move between the two alternatively. So this is a picture always to remember. B is this codimension 2 submanifold inside the ambient manifold N. And now we have a circle family of pages all having the same boundary, so moving around. So what you should think is I took my book and I opened it up and I glued the front cover to the back cover. And this is what you see. Okay? So this is some notion in the world of smooth topology. Now I want to input some dynamical system on top of my manifold. So I want to,
Back again. So how are the orbits related to this structure? The orbits are in.
I'll tell you now. So far, there's no orbits. There's no dynamics so far. Now there's a dynamics. So imagine that you have a flow on your manifold M. I will want to say that the open book is adapted to the given dynamics if B, this codimension 2 submanifold, is invariant under the flow. And moreover, the orbits of every other point are transferred to the interior of all pages. So this is where the dynamics comes in. In this situation, each page of the open book becomes what we call a global hypersurface of section. So this is just a high-dimensional notion of a global surface of section. Namely, it's just codimension 2 submanifold, codimension 1 submanifold, whose boundary is invariant, which is the binding of the open book, and the orbits of every point away from the binding meet the interior of each page transversely in the future and past. Okay. So in this situation, we also have a Poincaré return map a priori defined on the interior of each page.
When you say invariant, you mean invariant as a set?
As a set, not pointwise, but setwise. So I mean, it's already, you should think of a threefold in which there's a lot of interesting dynamics, but there's also sitting aside a fivefold where things are wrapping around. So the open book here, what's doing is guiding the dynamics. So I have this binding and dynamics is just wrapping around it. This is like a picture that you should have in your mind.
Do you have any assumption on how B looks like? Besides codimension 2?
So far, no.
Can it have similarities? Is it a manifold? Is it a smooth manifold?
It's a smooth manifold. Let's assume it's a smooth manifold.
And connected?
If not necessarily. In dimension 3, it's not. It's a bunch of circles. But in higher dimension, I mean, you don't have to. We're just usually going to be connected. Higher dimensions. Okay. So the notion of this open book, in some sense, goes back. So let me tell you a bit about the historical remarks of this circle of ideas, which are more or less classical. So the planar situation, what happens is after you regularize the collisions, as I said, you will get near the Earth and the Moon, the level set topological will be an RP3. An RP3 is a smooth manifold, has the structure of an open book with a page, which is the annulus, which is also the unit discotangent bundle of the circle in symplectic sense. And now the monodromy is the square root of dangerous along the belt of the annulus. Okay? So this is as a topological manifold, this is what it is. But now the hope is that since I have some dynamics in RP3, I would like to find a concrete vibration in this abstract type that is actually adapted to the given dynamical system. Okay, so now that it's been.
What is the RP3?
RP3, you should think of the level set near the Earth or the Moon. It's like you fix the energy, you've regularized, you compactified it. This is where the dynamics is happening. Okay.
Now we're trying to look at the dynamics in the six-dimensional case.
Yeah.
And how.
I'll get there. But so far, this is a planar problem. So from today's modern perspective, one can sort of interpret, roughly speaking, that this is what Poincaré did. He actually found an open book adapted to the given dynamic. So basically, this is a classical perturbative approach, where you start with some integrable system, you try to understand everything that's happened. Usually you can do that, at least in a qualitative way. Then your hope is, well, I perturb that integrable system, and then I try to study what remains. Right? So this is what Poincaré roughly did. So he started with a rotating Kepler problem, that's mu equals 0. He found a angular-like global surface of section, and then argued that the same surface of section persists after I perturb. So now mu is small, as long as the energy is subcritical. It's below the first critical value. Okay.
So that was a big Earth, a very small moon.
Exactly. So
And
this is a
even
very small.
smaller.
Yes. So the moon is gone, then you study, you find your angular-like surface of section. Your moon is very small, and you do the same. Okay, this is perturbative approach.
So what are the two binding orbits of that?
It's a Hopf link in RP3, so this is the direct and retrograde orbit.
The direct and retrograde.
Now, roughly 50 years later, in 1963, Conley did a similar thing, but for a different perturbative regime. So rather than mu is small, mu is whatever it wants to be, but now the C is very, very negative. So you're very, very close to the actual Kepler problem. So he also found angular-like surface of section, studied the return map, checked that it satisfies the classical twist condition, used Poincaré-Birkhoff, found plenty of orbits, right? So these are the long planar Conley orbits. Right? Also a very classical story. So now 1969, not so many years later, McGehee provide the same thing in the same perturbative regime that Poincaré considered, but replacing the angles by a disk. Okay? So this is a disk-like global surface of section. And then he actually computed the return map and used KM theory, found all sorts of interesting dynamical phenomena. So this is bits and pieces of the classical story, right? Very biased towards what I'm going to say, of course. One could organize a whole special year on the history of this problem alone. So, but yeah.
So the fact that you can have several topologies for the surface of section, is it clear that the surface of section is not rigidly defined by the problem?
Yeah. I mean, if you have a disk, I mean, there are ways of sort of adding topology to your surface of section. In some cases, where you want to find the simplest possible one. Right?
So the disk was the simplest. So,
yeah,
so
this is the simplest.
The analyst was like with some added topology, and it was able to reduce the disk.
And the topology of the surface of section that we'll find, I think it will be clear from the notion of the open book, which is a global condition, will impose restrictions on the topology of the level set. So you can't, if you want an open book with a certain page, you need to have a special topology. Okay.
Agustin,
yeah.
McGehee, was that in the 2-to-1 cover, the negativity regularization?
I believe that it goes down. I'm not so sure though.
Because you can't have a disk-like surface of section for
you can have a rational disk-like. So now the boundary is doubly covered when you project it down.
Oh, that's what he found?
I think, I mean, yeah, I'm not so sure to be honest. But, yeah. But I think that's the right picture. Maybe you're right. Maybe he wanted to double cover and did Levi-Cheat. That's probably what he did.
And was that result just for the circular problem or for the job?
For the circular problem. Okay. So let's take a very long step down the last century. So as far as I'm aware, everything that's non-perturbative in this problem, all the techniques that gives us something in this problem is based on foundational work by Helmut and Witkowski and Sandler. So this is holomorphic planes and symplectization. In this setting, what you usually consider is what's called a convexity range. So now you look at the set of all parameters mu and c with a subcritical c, and such that the so-called Levi-Tributary regularization, which is this thing that Kai is mentioning, of the planar problem gives you a convex problem. So the Levi-Tributary regularization is a regularization scheme for collisions, which compactifies the level sets, and it gives you a dynamics on S3. So the double cover of RP3. And so it lifts the dynamics to S3, and being convex means that this S3 sits as a convex, like as a boundary for convex domain inside R4. Okay, so this is the convexity assumption. And you should observe, that this is in principle a non-perturbative set of values. So it contains all the integrable cases, which correspond to the perfect S3 inside R4, but also contains dynamics which in principle are far away from being integrable. So this is a convexity range. And for this range of parameters, there's a theorem by Peter Albers, Fish, Frauenfelder, Helmut, and van Kurt, that in the convexity range, they actually give us global disk-like series of section for the dynamics. There's also a more recent result, 2019, I believe, by Chiniewicz, Salomon, Vysotsky, that also in the convexity range gives us an open book on RP3 adapted to dynamics. Okay. So this is as far as I know, all there is in the planar problem. There's also some related results that I'm not mentioning, but like this is for sure the latest result in this direction. Okay, so let me tell you then what the spatial picture looks like. So this is step one in the Poincaré picture. So find the global surface of section. So now we consider this regularized level sets. There's an energy hypersurface in the spatial problem. And the theorem that I proved recently with Otto is that for any mu, and this works really for arbitrary mu, there's no restriction on it. Well, the regularized level set, which is a copy of S3 times S2, actually admits an adapted open book to the given dynamics. And we pin down precisely the topology. So the page is now D stars 2, so a copy of the unit disk cotangent bundle of S2. And then the monodromy is the square of what's called the densidality, which is the symplectomorphism of D stars 2. So before we had D stars 1, and we had a square of a Dane twist on D stars 1. All I'm saying is that we replace D stars 1 by D stars 2 and the Dane twist by densidal twist. Okay, so I mean, I don't want to get too much into detail of what those things are, but the topology is pinned down.
Can you repeat what OB means?
Open book.
Open book.
So now we move to the generalization to the spatial case, right? Okay.
Okay, so I mean, the binding for this open book is actually a copy of RP3, which you should think as a planar problem sitting inside a spatial problem as a co-dimension 2 invariant subset. So you fix this works for every energy as long as it's in the low energy range. And the content of the theorem is that it reduces all the ambient dynamics on the starting FIFO on S3 times S2 to studying the dynamics of the return map, which is now a self map of D stars 2, and it preserves some symplectic form. And so reduce the problem to study a symplectomorphism of D stars 2 for some symplectic form. So this is the picture in high energy. So it's a very different question to study the sort of maps. And in some sense, that's the direction that I'm proposing as work in the future. So this is a picture to remember. So this ambient dynamics happening in S3 times S2, this Hamiltonian flow, which is actually a rate flow. And then we have an RP3 sitting inside, which is a planar problem. And then we have a circle family of D stars 2s. Okay. If D stars 2 sort of confuses if you're not used to the symplectic language, you just think of it as the unit disk tangent model of S2. Okay.
What is the symplectic form on D stars 2 that you're studying?
It's so you have some ambient contact form alpha. It's just a derivative of alpha restricted to each page.
Okay, but the alpha is
given.
something.
Yeah, it's whatever it is. It's giving you the dynamics. Any more questions?
Okay, can we think of D star S2 as sitting inside D star S2 with a standard form, but just in a complicated way?
Yes.
But fibrous star shaped?
Yes. Yes.
Okay.
Yes. There's another complication. The symplectic form degenerates at the boundary, but you know, yeah. Okay, so this is a picture to remember. And let me give you the basic idea of how you would prove such a theorem. And it's really based on a very simple observation. So look at the planar problem, which I told you is P3 equals Q3 equals 0. And now define a fibration taking values in the circle, which is what's written down there. So you take Q3 and P3, you cook them up into a complex number, you divide by its norm. This is obviously well defined away from B. And now this is a fibration of a circle, so it has an associated angular 1 form, which we write down very explicitly. So all you need to check is, well, compute the Hamiltonian vector field, giving you the dynamics, or the rate flow, or the rate vector field if you want, and then plug it into this angular 1 form. And then what you should get is some expression which should be non-negative and vanishing precisely only along the planar problem. And then you do this computation, this is what you will find. and then, well, you're almost happy because it gives you what you want, except for the fact of the obvious problem that it doesn't extend to the collision locus. So with Q equals C or Q equals N, these terms explode, so this computation doesn't work. So all the work in this theorem is dealing with the collision locus. Okay, what happens there is really very subtle. So what we did after you regularize, there's another open book which works over the collision locus. You need to interpolate with this one. This creates an interpolation region, and you have to be very careful. So it's a very long sort of estimate that you need to do. But in principle, it's basic math. There's no hardcore modern technique in this there. Yeah.
Is this problem can be somehow regularized when you take P3 and Q3 to 0 to get to the previous problem, to the planar problem?
That's a good question. No, I mean, in some sense, and this was very surprising to me, finding the global sources section, the spatial problem is much easier than the planar problem. And one of the reasons that, as Kai asked me, I mean, what's the invariant subset in the planar problem? This is a Hopf link. This is two orbits which are linked. And those are not given to you. You need to find them first. Here, the planar problem is given to you. Just drop the last two coordinates. So it's much more explicit, but you can do it by hand. In the planar problem, you can't do this by hand. This is why it took so long, in 2019 to find the open book. And not so terribly long to do this. But still, there are a lot of computations, but it could have been done many years ago. The insight came from other places like Giroux correspondence. Anyways, so let's try to interpret what this is actually saying, right? If you look at this vibration, if you look at the pi over 2 fiber, this corresponds to Q3 equals 0, P3 is positive. So it's everything that projects to pi over 2. Geometrically, all this means is you stand on the plane, which is Q3 equals 0, and then the third component of the momentum being positive, it means that you're shooting orbits up, right? So you shoot your orbit up, and then the primaries are going to attract your satellite, so it's going to come down. And then the same thing's going to come up again and down. And so this, qualitatively, what you're seeing is this sort of behavior, which translates when you do the open book to wrapping around the binding. So this is intuitively what's going on. And that works as long as you're away from collisions, right? If you collide, then there's a trampoline. The regularization schemes usually give you a trampoline, so you come back. So what this tells us is that the page, meaning shoot orbits up, is transverse to dynamics, means that the satellite intersects the plane transversely each time. This is the same thing as saying that the planar problem is invariant. But I mean, this is the geometric interpretation of this page being transverse to the given dynamical system. Okay.
So in this thing, you don't see the planar behavior at all?
You see it as an invariant subset. I mean, you don't see it in the Ambient open book. This is more adapted to the spatial problem. So this relates to what I'm going to say now. Like, let me see. So what you should note here is that the spatial orbits, those which are non-planar, so which are not contained in the planar problem, are in 1-1 correspondence to interior periodic points of the return. So in the interior of the D stars too. So they're wrapping around and not sitting inside the binding. So the goal, I mean, this reduces the original goal to finding infinitely many interior periodic points with arbitrary large periodic points, many orbits. Okay? So this is one of the goals that you could try to set for yourself in a concrete way. So with this in mind, actually with Otto, we also proved a fixed point theorem. So now we move to step 2 of the Poincaré approach. And using Floer theory, more specifically symplectic homology of the page, in this case the D stars too, but we did it more generally for any Liouville domain and so on. But I don't want to go into the details. I mentioned a special case in the short talk. But what I want to say is that we actually proved what you could say is a vast generalization of the classical Poincaré-Birkhoff theorem for what we're calling Hamiltonian twist maps. So this is a generalization of a classical notion of a twist map on the angles for arbitrary dimensions. This is, of course, a very nice and good thing. The not so good thing about the story is that we couldn't actually check the twist condition as we defined it in the three-body problem. So we couldn't check the condition that was very natural for us, especially from the perspective of Floer theory, in the problem that actually inspired the theory. So, and if true at all, which is very unclear, it seems actually very hard to check. So I'm not claiming that I could find infinitely many orbits. I'm saying that I have a theorem that could possibly do it. Maybe we need to adapt the definition of what a Hamiltonian twist map is. Okay.
Say what the condition is.
But the really sort of big picture of this whole story is that this opens up what it seems to be a completely unexplored line of research. So this is the study of Hamiltonian dynamics in high-dimensional Liouville domains. So a Liouville domain is an exact symplectic manifold with contact boundary. You should think of it as the page of the open book. where the boundary is a planar problem, and now you have some Hamiltonian map, and then you want to say something about it. Again, in a broadly understood sense, does it have invariant subsets, like points? Can I find some crazy chaotic behavior? It seems to be completely unexplored, as far as I'm aware. And you should think of this as a natural higher dimensional version of dynamics on surfaces. If you go down the history, right, dynamics on surfaces is a huge industry on its own right nowadays. So people have studied maps on Hamiltonian maps of the disk or Hamiltonian maps on the annulus and twist maps for a very long time. And this is of course inspired by the planar problem, because this is the page of the open book that you find there. So what I'm claiming here is that, well, the natural version of this story of actually doing dynamics on surfaces is doing dynamics on these dual domains, pages of open books. For instance, I mean, one concrete starting question that you can set for yourself is the following. So you start with the Hamiltonian maps that are generated by some Hamiltonian function of some open dual domain. So you should think of the page when I remove the boundary, so the planar problem is gone. I want to ask, does it have fixed or periodic points? How many? Do I need to impose conditions? So on and so forth. So you can think of the theorem that we proved with Otto as the version in this context of the Poincaré-Birkhoff theorem. But there's also many other two-dimensional analogs, for example, like the Brouwer's translation theorem, which is a statement about fixed points on the open disk for area-preserving map. And it gives you at least one of them. This is the topological picture. There's also a very well-known theorem of Franz from 1992 on the open annulus, so which gives you none from many on the annulus. You could ask the same thing in higher dimensions, and I think this is the proper sort of high dimensional notion. So maybe, these two theorems actually seem not to translate. Maybe the question is, what's the right version behind it? And this is especially interesting when W is a star-shaped domain in R2N, so something which is transverse to the radial direction, or more generally, if you know what this is, that it has vanishing Floer homology. There seems to be a fascinating interplay between interior and boundary orbits, which definitely should be looked into. And it seems very interesting at this point. But again, it's very broadly unexplored. Okay, so far this is the story of trying to find orbits in the planar and the spatial problems. So, I talked about step one, which I think we fully generalized, and I don't think you can do any better than what we did. And then step two, of course, there's a lot of stuff to do. But in this process, we managed to find some new perspective, which I'm calling pseudoholomorphic dynamics, which should be understood as a subset of what Helmut calls symplectic dynamics. And what I mean is the pseudoholomorphic dynamics, you should think of as dynamics on moduli spaces of pseudoholomorphic curves. Okay. The key construction that I want to sort of explain a bit now is what I'm calling the pseudoholomorphic shadow of the original dynamics. So I have some dynamical system. I will associate another one in a different manifold which captures some of the dynamical information of the original problem. Okay. So the philosophy is the following. So, if you have some complicated higher dimensional problem which you're trying to shed some light on, then the first thing that you should try to look is the shadow that your lantern is producing. Right? So if you have a higher dimensional object, usually you project it down to lower dimensional spaces in order to try to study it, and maybe the projections to remember something about the original object. If you have many projections, then all the better, because you can see it from different angles. So this is, roughly speaking, the philosophy of what I'm going to tell you. So, and this philosophy starts with the following topological observation. So the page of the open book, this D star is 2, admits a leftist fibration with annular fibers. So a leftist fibration is a fibration except for the fact that it may have some singular fibers. And the singularities of the fibers are very constrained type, they're nodal singularities. Okay. So this is a picture to remember. It's a bit complicated if it's the first time that you see it, but this is the standard leftist fibration on D stars 2. So what you're seeing here is a projection. So the whole space is D stars 2. You're projecting down to the circle, to the disk inside the complex plane. The regular fiber of this projection is an annulus, except for the fact that there are precisely 2 singular annuli. And here's a zero section of D stars 2. And these singular fibers intersect the zero section precisely at the north and the south pole. Okay. And the boundary of this picture is a copy of RP3, it's a unit cotangent bundle of S2 with its open book that I told you about before. And this open book is very naturally obtained by taking the boundary of this whole vibration, this whole structure here. And for example, RP3 you can think of as the tangent bundle to S2, the unit tangent bundle of S2. And in this setting, there's this very well-known Birkhoff annulus, which is you sit on S2, you sit on the equator, that's a circle. Now you look at all the vectors that point to the upper hemisphere, that's an annulus, that's a Birkhoff annulus. And what I'm saying is that it appears precisely as the fiber over the complex number I in the base. So this is a Birkhoff annulus. And then the opposite Birkhoff annulus, which is what you see at minus I, is those vectors which point to the lower hemisphere in RP3. Okay? So what I'm saying is that all the sort of classical annually and all the classical topological objects appear also in this picture already. So I think this is the correct high-dimensional version of all the stuff to look at. Okay, so this is the structure that you have on the page, right? So this is a 4-dimensional manifold, so D star is 2. But now we're working on a 5 manifold. This is the hypersurface of section. So what's going on is that, well, I have this left variation which projects down to the 2 disk, but now I have a circle family of this guy. So I need to hinge the boundary in place. So this is a planar problem here, and I need to move it around. This traces out my 5-fold, my S2 times S3. And if I apply the left iteration on each page, this traces out to quotient, which is nothing else than S3. Because it has an open book. This S3 is the only manifold with an open book whose page is a D2. The monodrom is necessarily isotopically identical because of the mapping class group being trivial. So you see the quotient is just S3. So you can think of like the moduli space of fibers is a copy of the 3 sphere, or the leaf space of the foliation is a 3 sphere. So this is sort of the underlying topology of the product. This is the level set that you're looking at. Okay. So in this context now, we have this so far, this has been, again, a discussion of what's the topology of the level set. Now we have some dynamics, right? This is a rate dynamics. It's given by the dynamics of a contact form, alpha, which is whatever it is. So I want to consider the space of all rate dynamics adapted to my open book, adapted in the sense that I defined before. The theorem that I can prove in this context is, well, that the shadowing 3 sphere inherits the dynamics from the original one on the 5-fold. Okay? So any given alpha adapted to dynamics on the 5-fold induces a dynamical system in the quotient, which is intimately related to the original one in a suitable sense. So the idea here is that these annuli are actually holomorphic annuli. So there's some holomorphic curve machine that gives me this foliation, and they're adapted to the given alpha. And this is what's important. Adapted in the sense that, you know, alpha is a 1 form, the derivative of alpha is a 2 form. If I restrict the alpha to each annuli, this is an area form. So it's positive on each angle. So I can integrate my vector field along this area form, and this gives me a vector field on the quotient. This is the shadowing dynamics, roughly speaking. Okay? So it's obtained by integration along the annuli, and you can think of it as an L2, a suitable L2 projection of the original dynamics to the tangent space of the moduli space. So, you know, in this picture we have a return map, right? So the dynamics is transferred to, so it comes back. The return map might or might not preserve the foliation. There's no reason why it should. It does that in integrable system, in the case of the integrable system that we have. But in general, it might not. It might just send an annulus to some other annulus, which is not the original in the original foliation. So what I'm saying is that this shadowing dynamics is the best approximation with the property that preserves foliation. So I take my original dynamics, and there's a way of projecting it down to the tangent space of the moduli space. So now it sends an annulus to another annulus. In other words, the dynamics on the quotient, on S3.
Is this a property of the particular alpha or like for any alpha?
For any alpha, it's a property of the space of contact forms in which it is contained. It's a particular property of what the topology is.
So that's why for any alpha, you're getting this projection.
Yes. This is for any alpha. And this is something the strength of the theorem. Okay. I don't want to apply to any alpha. I would like to apply to the 3 alpha.
Can you understand this quotient dynamics in special cases like for Hill's lunar problem?
This is one of the questions that I want to answer at some point. I can understand it in the rotating Kepler problem. The projection is just a Hopf law.
Right. Yes.
But then, you know, okay, but the projection of a Katok example, which is a very famous example, is a rational ellipse law.
Yeah.
So, yeah, I understand some non-trivial examples. But okay, let me get there first. Okay, so this is the shadowing dynamics. So this is the holomorphic shadow.
Can you repeat again how you get the shadowing dynamics? Can you just because
yeah, so we have alpha, which is a contact form. Now I want to define this alpha m on the quotient. So I sit on an annuli U. I want to define a 1 form on the moduli space. The point on the moduli space is an annulus. And now I plug in a vector field, which is a vector field along the annulus that defines some linearized Cauchy-Riemann equation. And all I do is integrate with respect to I do the original one applied to V, view it as a vector field. So let's say set in U. This is V of set, and then I integrate with respect to the alpha restricted to U. But it is. It is because I understand the foliation explicitly. So I can tell you what its symplectic complement is.
So in particular, you're saying you start on one of those annulus fibers, and you come to some other annulus, and you start at a different point. You come to the same, but it doesn't matter which point you start.
Well, it's unclear to me what's the. I mean, yes. I mean, now you have.
But you say the dynamics projects, right?
Yeah.
So it means it doesn't matter which.
The maps and annulus,
you always come to the
so
same.
if you take two different points in the same annulus, it will get mapped to
The same.
the same annulus.
Can I understand this dynamically? Why is that true? Because it's some very specific property of these.
But yeah, it's a very specific property of the topology. I construct the foliation, right? Foliates everything, so I can actually. I mean, this is what it is. I mean, this is actually a one point in the moduli space by construction. So I integrated along the fibers, and I'm saying that.
Is it true for any Lefschetz fibration or just for this particular?
What I'm using about this structure is that the fibers are genus zero. So it has to do with moduli spaces and analysis.
We're very using this fact.
The fact that I can construct the foliation. So this has to do with, for example, Wendel's work. So if you have a holomorphic open book in RP3, then one of
But in this definition, we don't use any kind of homomorphic.
No, this is a general definition, but the fact that it's a contact form, yes, depends on the specifics of the foliation. This is not for any foliation. This is for this specific situation. This is my claim.
And you cannot say what is the reason behind this? What is specific about this?
Yeah, what's specific is that I understand precisely the symplectic complement of each angle. So what you need to, okay, in general, this might not give you something whose derivative is which is a contact form in the moduli space, because you don't have control on the symplectic normal bundle to the curve. In this specific case, I have all the control in the world. I can understand the geometry of the foliation precisely. I mean, this is a very subtle point, but yeah, I mean, this is non-trivial.
You said that fibers are genus zero. Which fibers?
See what?
You said you're using that the fibers are genus zero. So which fibers?
The diagonally. The annually are genus zero. If you replace the annually by any other genus zero surface, the claim is that this also works.
Okay.
Let me just move on because I have time constraints. So, so we have the dynamics being transversed to each page, right? The satellite is doing whatever it's doing here, and now I'm projecting down to this S3. So I could do two things. I could average, as I told you. I get some vector field which is transversed to each page, or I can not do that. I can just directly project to the moduli space. So this doesn't necessarily give me a line or a flow. It gives me a cone structure. So it opens up to a cone. And the geometry of the situation implies that the cone is transferred to all of the pages and also to the contact structure in the moduli space. So, you know, what you're doing is you're seeing the orbits playing around here, and then you're looking at the shadow in S3. So this is like what you should remember about the topological and dynamical situation. There's some foliation, there's an open book. I mean, it's already quite rich in this sense.
But say periodic orbit of the system downstairs have very little to do with periodic orbit.
In principle, yes. So an orbit, yeah, this is the problem. This is not a precise, this is not, it has several disadvantages, right? The thing is that I'm actually changing the dynamics. So in principle, I don't have much control between the relation between the orbits upstairs and orbits downstairs. All I know that the orbits upstairs project down to orbits of the cone structure. In principle, the shadowing vector field might have plenty of close orbits, and it should, because of results in dimension 3. It's not clear how much of that I can translate to what's going on upstairs. So this might not be very well.
Is this related to your previous comment that you can't check your condition? You had a theorem which you said that even to check it for specific numbers, in the real world, you couldn't check your condition. And I couldn't understand what kind of condition that would be. Is it related to this point?
No, it is not. I mean, it's a different problem. So the condition, I mean, I didn't define it, but it has to do with finding a generating Hamiltonian with a specific property at the boundary. So it has to run in the direction of the dynamics at the boundary. This is it's a different problem.
So it's not something that you know is generically true or anything.
Yeah, no, and there's no reason why it should be.
I see.
There's some freedom in definition that needs to be explored, but this one is rather unclear what's it. If this definition is not suited, what the actual definition should be.
And when you're doing a perturbation, is it clear that you have this condition?
Also not clear because it's not even an open condition. This is a proper definition.
Okay, thanks.
Yeah. Okay, so globally, what you can define is what I'm calling this holomorphic shadow map. You just take the shadow of the original flow upstairs in a specific space of dynamics. Right? So I precisely pin down the space and I project it down to some flow on S3. The theorem that I can prove is that this map is actually surjective. So what this means is that you give me any dynamics on S3 adapted to the open book on the quotient, I can realize it as the shadow of something. Okay? So you should think of this as a statement about the complexity of the problem. So dynamics in S3 is very well known to be quite chaotic and difficult already. What this tells you is that rate dynamics on S2 times S3 is at least as complex as dynamics on S3. So it's a concrete measure of the high complexity that you're dealing with here. So yeah, this, I don't know if this is good news or bad news, it's what it is. But the new program is in sense try to lift what we know from dynamics on S3 to dynamics on the 5. The orbits might be a bit subtle because of the reasons that I just told you, but maybe there's some other things that still survive, like entropy, things which are more coarser than just orbits. This is my guess. I don't know.
If you play this game 1 dimension down from 3 dimensions to 1 dimension. When you play this game down from 3 dimensions to 1.
Yeah, but you get the circle.
Yeah, but what do we get actually?
You get just a circle moving around. So the planar problem under this shadow map projects down to the binding of the open book here. This S1, this is just an invariant S1. You need to reparameterize the dynamics, right? So now what you're seeing is this open book at the planar problem. You have to reparameterize a time, and so now it maps page to another page. So it projects down to a simple sort of circle. It's an orbit of the shadow.
Can you see here to actually kind of how it's moving? Because there is, of course, pages are not preserved. So
we can reparameterize it.
What's the meaning? So so there is some kind of average point of the fiber, or what it is?
Yeah. So if you reparameterize time, you can achieve that the page gets mapped to a page. And then whatever happens in the page itself is a different.
Are you reparameterize time?
Yes, I have to reparameterize to define the shadow. Okay. So this is what happens in the three-body problem. So here is the convexity range, which is a subset, non-perturbative subset of the low energy range. And well, the claim is that for each dynamics in the three-body problem, this gives me an element in this space, and it has a well-defined shadow. But I can only get up to the convexity range. It's not clear whether I can get it all the way in the low energy range. And the integrable final is a rotating Kepler problem. The integrable system projects down to the integrable system in S3. This is the Hopf flow. You're just moving around the fibers of the Hopf fibers. Yes, this is the picture.
Do you know, like when two things project to the same thing, can you say anything?
Not much yet. I mean, it's like they differ by what happens on the fibers. Well, I mean, this is a projection, so you forget a lot of information.
Yeah.
So for example, like all the different rotating Kepler problems project down to the same thing. The actual geodesic flow in S3 for the round metric projects also to the Hopf flow. So you get very different dynamics projecting down to the same thing.
Okay.
It's like, this is a simplifying projection. Right? It's still quite complicated what you see.
Yeah, but there's no good way of saying if they project to the same element, they have some.
I haven't thought about it all that carefully. Okay, so let me move on. So this has been so far a discussion of the theoretical aspects of the problem. I also mentioned in the abstract that there's some practical aspects of the problem. Of course, I mean, there are many ways of looking at the three-body problem, but one of the practical applications of this has to do with space mission design. Right? So if you're an engineer trying to send some satellite to place an orbit around the planet, you're looking at a restricted three-body problem. If, for example, the planet has a moon orbiting around it. In the context of actually finding conditions suitable for life outside of Earth, so this exploration of ocean worlds, there are actually two large missions which have been proposed by NASA. The first one is this Jupiter-Europa system, so trying to go to Europa and see whether there's conditions for life there. The same for the Enceladus, Saturn Enceladus system, which is a moon in Saturn. NASA is actually currently designing a spacecraft, this Europa Clipper, to put in orbit around Europa. So, I mean, I'm sure you will agree this is more than enough motivation to study orbits for this specific system, so which are restricted three-body problems with specific mass ratios for the purposes of optimization, right? So if you're an engineer, you want to optimize the orbit for flight time, for use of fuel, which is very expensive, and plenty of other practical things, which me as a mathematician escape me at this point. The following, what I'm going to say is work in progress with Urs Frauenfelder, who's joining us, who's a mathematician from Germany, and Dayun Ko, who's a navigation engineer at JPL and NASA, who's also, I believe, joining us online.
You want to minimize the mass of the satellite?
No, I mean, I guess. I mean, I want to minimize the use
So
of.
you're not assuming that it's 0 or something, right?
Yeah. I mean, you model it as being a point part.
Okay.
You want to find the best orbit to put it in flight around the planet for whatever reason that may be. Okay. The philosophy for us, that's coming from the theoretical aspects, is well, extract simple invariants from very complicated theories like SFT or Floer theories, but geometry, which are amenable for practical implementation. You can sort of give it to an engineer, but put them on a computer and actually get something useful. So concrete motivated questions or related classification.
Problem with this Europa, you're completely ignoring sun. Sun is irrelevant.
Yeah, sun is relevant. The sun is, there's no sun in my three-body problem.
And doesn't Jupiter have other moons?
It certainly does.
So depending on no, I mean for certain computations, sometimes you just look at a two-body problem, sometimes at a three-body problems, and for certain things you look actually also includes the sun in it, like whatever.
Yeah. I mean, yeah. This is an idealized world, right?
I mean, yeah, and then for the little difficulties you use some fuel.
Exactly. So you always correct on fuel.
Lack of transversality always by fuel.
Anyways, so there's a natural question of classification, right? If you want to optimize amongst all possible orbits, you want to know that whatever orbits your algorithm found, giving you different orbits. So at least from a qualitative point of view. So, two orbits are qualitatively the same if there's a one parameter family of orbits running them and nothing happening to. If not, they're qualitatively different. There's also a related question is cataloging. Can we actually construct a database of all the known orbits, all qualitatively different, or known bifurcations between them? It could happen that at some point your orbit bifurcates into a bunch of orbits, for example. And this is an interesting phenomenon. There's also practical tests in the line of this philosophy. Can we use symplectic invariants to test the accuracy of the algorithms and to guide or organize numerical work? And so provide some sort of theoretical groundwork for whatever the algorithm has produced. So this is sort of big. And it turns out that in practice, many of the orbits that are found numerically are symmetric. So there's several symmetries in the restricted three-body problem. For example, it was preserved by the anti-symplectic involution, which I ran down there. So it's a map from the T star R3, which is just a copy of R6, which is what's written down there. Just put a bunch of minus signs. It preserves the Hamiltonian given the three-body problem, but it anti-preserves the symplectic form. The fixed point locus, when you look at all the fixed points, is actually a Lagrangian subset of T star R3, so the symplectic form is 0. So a periodic orbit, we say it's symmetric, well, if it's invariant under the involution up to time reversal. So in particular, at time equals 0 or half the period, it's lying in the fixed point locus of the involution. So this is a picture to remember. The orbit is symmetric and intersects the fixed point locus precisely in two symmetric points. Okay, so what happens if you linearize the dynamics, right? If you linearize the Hamiltonian flow along an orbit, you will get a bunch of symplectic matrices. If you have a symmetric orbit and you choose to linearize the dynamics precisely at an intersection point of one of the symmetric points, you will get a symplectic matrix, which is a very specific one, which I write down here. Depends on 3 blocks, A, B, C, and it satisfies certain equations, which ensure that that the matrix is actually symplectic. So this is a subset of the space of the group of symplectic matrices, which we denote by SPI. And that comes with a GLN action coming from choosing a basis at the tangent space to the Lagrangian fixed point. Okay? So there's some set of symplectic matrices which are very nice. And before I tell you a bit about bifurcations, I need to tell you or remind you what the spectrum of the symplectic matrix looks like. So if you give me a symplectic matrix and I look at its eigenvalues, they come in different types. They have some symmetries. So you could have a positive hyperbolic pair. So mu is real and greater than 1, then it comes with a brother, 1 over mu. The same thing, you could have a negative hyperbolic pair. So mu is negative and less than -1. It comes with a brother, 1 over mu. So, but you could also have elliptic pairs. So lambda is in the unit circle, and then its conjugate also lies in the unit circle. But all you could, the last case is where your eigenvalue lies away from the unit circle and the real line. So you have a quadruple, a non-real quadruple. Okay, so this is a type of things that you see in the spectrum of the symplectic matrix. And so in terms of bifurcation, so bifurcation you used to think is, well, I have my orbit here, and then I move the energy, and it comes with on a regular cylinder. At some point, some catastrophe could happen, and your orbit becomes non-degenerate. It could split into a bunch of orbits. So what you're seeing here is bifurcation by definition, if you want, is that the eigenvalue 1 is being crossed in a one-parameter family after you regularize. So you get a bunch of symplectic matrices, and the eigenvalue being crossed means something's happening. In this case, which I took from a very classical book on Foundations of Mechanics by Abraham and Marson, it's a period doubling bifurcation. So what you're seeing is the elliptic eigenvalue of this orbit at some point transitions the number -1. So -1 squares to 1. So this means that the double cover of the orbit bifurcates. So you see that it spits out another orbit whose period is double the period of the original one. So you have this elliptic orbit popping out. So it went from elliptic, from transition to negative hyperbolic. So this is a period doubling bifurcation. I need, in order to introduce what I'm going to say, I need a bit more theory. So this is if you have an action of a Lie group on a manifold, then the GIT quotient associated to this space that you get when you identify 2 points, if the closure of their G orbits intersect. So if you just look at the quotient, usually there's some bad space because usually it's not a Hausser, so it has some non-separated points. This GIT quotient makes it Hausser. So this comes from algebraic geometry. You remove some bad points. Anyway, this is some topological technicality. But in this context, I want to introduce what we're calling the GIT sequence, which is something that we put up last month with Urs. And it's a sequence of maps and spaces. So if I linearize the dynamics at a symmetric orbit, I told you get one of these matrices, and it comes with this GLN action coming from choosing a basis. So I look at this GIT quotient. And then if I linearize at any other point, I get a symplectic matrix, and choosing the point doesn't change the symplectic conjugacy class of the matrix. So I get a well-defined point on this GIT quotient, where SPN acts on itself by conjugation. Similarly, I can look at this GIT quotient with GLN acts by conjugation on the space of matrices. It turns out this is a copy of Rn. You take a matrix, you map it to the coefficients of the characteristic polynomial. This gives you a diffeomorphism. Okay, so you have this sequence of maps. Now you look at one of these beautiful matrices, and now you can either look at it in this space or in this space. And then the third map is you project the first block, this A. So this is a GIT sequence. Okay? But okay, you can complain now because this looks pretty abstract. I told you there's some practical aspects of this whole story. The key point, however, is that first of all, any cylinder of symmetric orbits gives you a path in this space by linearizing at the symmetric point. So in particular, it gives you a path in all the spaces in the GIT sequence. The topology of the GIT quotients forces bifurcation sometimes. So this is what we do in the paper with Urs. We precisely tell you what the topology of this space is, of this space also. We know what the topology of this space is, and we tell you what the maps are doing. Turns out that these are branched manifolds, and you can understand precisely the topology. They come to some bifurcation locus, and then when you remove the bifurcation locus, you get a bunch of connected components. And by construction, if you take two orbits which lie in different connected components, they cannot be joined by a regular cylinder. So that's what we're trying to do. Impose topological obstructions to the existence of regular cylinders of orbits. So this is the picture that you should remember. So this is n equals 2, which is the dimension relevant for the spatial problem. What you're seeing here is that this is the base of the GIT sequence, this R2. And the map is very, very easy. It's actually, you take a matrix and look at its trace and its determinant. These are the coefficients of the characteristic polynomial, basically. So we can put it in a computer record. And what you're seeing is this branch locus. So here you have the bifurcation, the period doubling bifurcation, which corresponds to matrices with eigenvalue -1. Here's the bifurcation locus, eigenvalue 1. And then all the other sort of regions are labeled by their type of eigenvalues. So, remember we're in dimension 4 now, so we could have two pairs of eigenvalues. For example, you could have an elliptic pair and a negative hyperbolic, or you could have a doubly elliptic pair in this region. So when you linearize and you look at the path, for example, the period double bifurcation is you started here and then you cross the bifurcation. So this is the basis of the GIT sequence, and you should think there's two spaces lying on top of this, and they're actually branched manifolds, and the covering degree varies from component to component. And we tell you precisely what the covering degrees are like that. There's some more information, but I'm not going into detail. So I'm already running out of time here, but let me just move a bit faster. So in the philosophy of trying to extract simple invariance from complicated theories, we could look at what we're calling the SFT Euler characteristic. So if you give me a Hamiltonian orbit, it has what's called the local Floer homology associated to it. I will not tell you what it is, but it's some algebraic gadget. Roughly speaking, you have an orbit, which might be degenerate. You perturb the Hamiltonian, now it spits out a finite number of non-degenerate orbits, and then you do this computation here with this Euler characteristic. You count the type of each orbits that you see, you do this sort of computation, which is very, very simple, and you can put it in a computer. And the key point, this number is invariant before and after bifurcation. Okay? So it is easily implementable on a computer. So it serves as a test, right? So if you're in a day and trying to find your orbits, if you can see that there's a bifurcation happening, the eigenvalue is 1 is being crossed, you do this computation, which is easy. And then if it stays the same, good. If it differs, then you know you missed an orbit. So you should find that orbit. So this is a very simple test for the algorithm that the engineers are producing, coming from Floer. For example, something that this invariant tells you is that imagine that you have a symmetric orbit. Well, a period it could bifurcate in two different ways. So it could bifurcate at this point, this case, or at this point, the other case. And there's no preferred choice. But the invariance of the Euler characteristic tells you that it can only one of them can actually happen. So this is actually useful when you're actually trying to find the orbits. You see some period double bifurcation, you wonder, is there another one that I'm missing? Turns out that the Euler characteristic tells you that you're not missing it. So here's an example that de Jong produced numerically. So this is what you're seeing is what I'm calling the snitch configuration, because I grew up with Harry Potter. And this looks like the snitch to me. I don't know what people call it, but this is what it should be called. But the Jupiter-Europa system is mu corresponding to this large number here. And this is found by what's called the cell mapping method, introduced by some algorithm introduced by the engineers. So you're seeing this orange planar orbit bifurcating into spatial orbit whose period is double. And this is, for example, what it looks like in the GIT quotient. So, we compute what it's actually doing on the plane. So as it should, this is a plot that tells you that it's going before bifurcation from the doubly elliptic region to the elliptic negative hyperbolic region, crossing this period double bifurcation locus. And the color change happens precisely at bifurcation. So this is all produced numerically. So the goal is, well, maybe we can do the same thing for all the orbits that we know. Construct a database of symmetrical orbits and the bifurcation. It's a cloud of dots in this plane and this GIT quotient. Anyway, so this is actually one such example. So let me close with a bunch of remarks. So I hope remarks convince you on something that is still a very, very, very interesting problem to look at even today. And sort of the interplay between the theoretical and practical aspects are really fascinating. And they give very different perspectives on the same problem, but sometimes inform each other. So you learn something about the numerics that has to be explained in the theory guides the numerics, and so on. I mean, this is not only the restricted three-body problem, this is a very general phenomenon in science. The second remark that I want to make is to have some new geometric and topological scaffolding around the problem, like the Openbook, the affiliations. What Helmut likes to say, we found some sort of order in the chaos. And we also have new theoretical and practical perspectives. So the shadow, maybe there's something there, and the practical implementations of GIT sequences and so on. The question is, well, how can we actually use them to extract new dynamical information? So this is very sort of very unexplored. And perhaps this is a good time to come back to the orders. Thank you.
Which origin you want to revisit?
What?
Which origins you want to revisit?
The three-body problem. That's a good question. I mean, in some sense, like, okay, the three-body problem was like the first dynamical system. I mean, all of them, maybe I'm exaggerating, but like all the theory of modern dynamics can be probably traced to work of Poincaré, for example, on this problem alone. Surface of section, the Japan of exponents, the questions of entropy. I don't know. So this is what I mean by the origins. And also Floer theory comes from this problem. The first theory is the Arnold was designed to prove the Arnold conjecture, and the Arnold conjecture is directly inspired by the Poincaré-Birkhoff theorem. Poincaré-Birkhoff theorem, I already told you, is what appeared in this problem. So that's the origins for me.
Have you thought about having, if there are more bodies? I mean, of course it gets complicated, but.
I mean, no, I mean, maybe you can just adapt many of these things. I mean, the good thing about this problem is that in some sense universal. So whatever you find in here usually translates to other problems. I don't know. I mean, I don't want to make a very general claim, but we also found this open book for more general Hamiltonians, not necessarily many body systems, but what are called like Stark-Zeeman systems. So you have some other terms in the Hamiltonian, and this open book's always there, which makes it pretty universal in some sense.
So can I understand something here? The search for periodic orbits, in that search, you're not claiming anything. You're saying that this open book decomposition opens doors to study many other dynamical issues related to the three-body problem, rather than just periodic orbits. Is that correct?
Yes. I mean, what my claim is that, okay, now there's a return map, right? The return map encodes all the dynamics of the problem. This is my claim. And whatever you can say about it says something about the original problem, in particular periodic points.
But so far the success has been more in the direction of other aspects of the dynamics. I mean, periodic orbits aren't everything.
Yeah, I agree. I mean, but I think it should be the starting point.
Okay. So then let me get back to your funny condition that you couldn't verify, which sounds, can you say more about that?
Yeah. Can you see this board?
Yeah, I can see it. Thank you.
So imagine like W is V star is 2 if you want, or some Liouville domain. So W is some manifold with a symplectic form. It's exact, so it's T alpha. So now you look at alpha restricted to the boundary. This is your contact form, lambda. So this guy has a ray vector field, R lambda, defined by lambda. Lambda is 1, and the lambda 0. So this is the rate dynamics associated to the contact form. So the twist condition as we define it is you have a Hamiltonian, W which might depend on time. So let's say this time coordinate is t. So the condition is just that if I look at the Hamiltonian vector field and I restrict it to the boundary, let's call it B. This, I want it to be a positive multiple of the ray vector field. So HT R lambda, and this is positive. This is a function on the boundary B.
Mm-hmm.
So if you look at this definition, if W is just the annulus, then this condition is the same thing as moving. I mean, if moving positively in both boundary components means moving in one direction and the opposite one in the other one.
Yeah, that's
just
right.
the orientation. So this definitely generalizes the classical notion.
Yes.
The problem now is that this is a huge, I mean, the dimension of B could be very big. So there are plenty of directions to move. You could be transferred to the contact structure, for example, as opposed to this more restrictive condition.
Mm-hmm.
But it's also not open, right? Again, because there's a lot of room.
But do you have examples where it's interesting?
Yes.
Where it's true and interesting?
Yes. Well, we have examples that we cooked up. Maybe they're a bit artificial. But you definitely have examples. And I can give you non-examples too. But the Katak example is a non-example because it only has finitely many orbits.
Okay. Yeah. All right. I think that answers my question there. Thanks. And we were having trouble asking questions before, but now it's working very well from the Zoomers. Yeah. Thanks.
Are there other questions in the chat?
I can ask you a question. So when you do these regularizations, so you run the risk of introducing, I don't know exactly how it works, that's what I'm asking. So you run the risk of introducing like fake periodic orbits, or does it work?
That's a very good question. The fixed point theorem that we proved goes through introducing a priori garbage that you don't care about, and then you need to throw away the garbage. So I can tell you a bit about the proof. Like it uses, we have this condition here, we have some Hamiltonian, you want to find orbits in the interior, but then you need to, your force, in order to do symplectic homology, the Hamiltonian needs to be very specific at the boundary. So you have to extend it in a suitable way to make it admissible for symplectic homology. But now in this extension, you run the risk of adding a ton of nonsense that you don't care about. So you need to impose another condition to rule those contributions out. So this is what we call the index positive condition. So the index of stuff here grows and you don't see it. I mean, yeah, that's a problem.
Okay. I have a question / comment sort of. So one thing that's kind of interesting about this this specific open book, the T star S2 with the squared gain twist, is that it's sort of fragile in the sense that if you perturb the symplectic form a little bit, it actually just becomes isotopic to the identity polymorphism. I wonder if this could somehow be useful for generalizing this twist condition. I mean, in fact, you can actually, in some sense, you can do the perturbation just by perturbing your Floer theoretic invariance instead of perturbing the map itself. So it seems like Floer theoretically, then it would behave essentially like having the identity as your monodromy map.
Okay. I mean, yeah, that might be useful. I don't know. I mean, it's something that we could discuss for sure. It's a very good point to stop and go to coffee break and discuss. Thank you.